Hello everyone, I'm Jianyu from Imperial College London. Our paper mainly introduces the implementation of object surface reconstruction using a structuralized system. Intraoperative tissue surface shape is a key point for computer-assisted surgery. It's a prerequisite to integrating multimodal imaging modalities for surgical navigation, and it could be used for pathology detection as well. In order to measure the tissue surface shape during the laparoscopic surgery, previously our group has developed a structuralized system with a miniaturized probe which can be inserted through the biopsy channel of a standard endoscope. This probe projects a light pattern of randomly distributed spores with different color. Once those spores are identified, together with the calibration parameters, the object surface can be reconstructed. In order to improve the applicability and the accuracy of this system, we developed an algorithm based on self-calibration which enables a freehand manipulation of the probe, and we also managed to incorporate the local norm information into reconstruction to improve its accuracy. Here is a brief introduction to the reconstruction procedure. Firstly, pre-calibration is carried out to find the intrinsic parameters of the camera and the probe. Then the structuralized system undergoes highlight removal and image smoothing. This is followed by a light pattern decoding step in which the projected spores are segmented and identified according to the color and neighborhood information. Till here, the object surface can already be reconstructed sparsely if the relative position between the probe and the camera is known. However, in clinical applications, the relative position between the probe and the camera can change from time to time, and applying a normal calibration to determine the relative position once it changes is time-consuming and infeasible. So we propose to use the self-calibration method for surface reconstruction. Assume a point X with its two projections on the two image planes XP and XC. Then XP and XC can be linked by a fundamental matrix F. With multiple correspondences, F can be estimated. Then the relative position can be estimated as well. This is then followed by a feature matching refinement step, which iteratively updates the epipolar constraint and the correspondences. Finally, the object surface can be reconstructed up to scale. Another contribution of this work is the incorporation of the local normal information in reconstruction. Given that the projected spores are very small, we made an assumption that the individual spores are located on individual local surface planes. So the image coordinates on the two image planes can be linked by a chromographic matrix H. Our assumption also permits a deduction that the spore shapes on the camera image plane should be ellipses, since they are the projections of ellipses from the probe image plane. Since that the ellipse parameter of matrices CP and CC can also be linked by H, and the orientation of local surface planes can be estimated according to H and the self-calibration results. By solving an optimization problem, we can find the local surface planes. Then the estimated normals are used to constrain the orientation of the local surfaces near the spore centers. The self-calibration reconstruction was tested by experiments on silicon heart phantom, ex vivo porcine liver, kidney, heart, and in vivo porcine large bowel. The reconstruction errors were measured using the surface distance after registering the reconstructed surfaces from self and manual calibration methods. From the bar chart, it can be found that the median values of the maximum distances are below 2.5% for all the objects except for the large bowel. This is due to the strong light-tissue interaction in the experiment. Since the normal information doesn't benefit the reconstruction of objects with smooth surfaces much, we only provide some intuitive results for the normal estimation algorithm on box corner, cylindrical object, and liver phantom. The benefit of incorporating normal information is demonstrated using a step phantom. Figure G and H shows the improvement of reconstruction by incorporating the normal information. In summary, based on the previous structuralized system, we developed algorithms to aid the reconstruction procedure to make it more practical and accurate. Our contribution mainly focuses on two aspects: the self-calibration methods, which enables a freehand manipulation of the probe, and the incorporation of the local normal information, which enhances the reconstruction result. We are currently working on the real-time implementation of these algorithms, and more experiments will be carried out to validate the whole system. So that's all. Thank you for your attention.